Okay, Assalamualaikum and good morning. This is our sixth lecture videos. So we continue with our chapter 1, multi-stage compression refrigeration cycle. Okay, this multi-stage type uh, is quite different with the cascade system that we have learned before, uh, because this system uh, it also has the upper cycle and the lower cycle, similarly to the cascade system, but it used the same fluids for the different stage here, the upper stage and the lower stage. Okay, it is different compared to the cascade cycle because the cascade we use the entire separate system between the upper and the lower cycle, but for the multi-stage it integrates all the system using only one type or the same type of refrigerant. Okay, but the multi-stage also has multiple compressors. Okay, by looking at this diagram, we have high pressure compressor at the upper stage and the low pressure compressor at the lower stage here. And then we have a flash chamber to separate the vapor refrigerant and the liquid refrigerant. The vapor will enter the mixer here with the other superheated refrigerants that comes from the low pressure compressor. Okay, and the remaining liquid in the flash chamber will pass through to the expansion valve in the lower stage, and then at stage 8, at the exits of expansion valve, it will absorb heat from the refrigerated space, and then it will change into the vapor type at state 1. Okay, state 1 is the inlet to the low pressure compressor here. Okay, and then the refrigerant from the state 1 will be compressed by the compressor at lower stage, and it will change into the superheated with high enthalpy value. Okay, and then the refrigerant here will mix with the vapor refrigerant from the flash chamber, and it will compress by the second compressor, which is we call high pressure compressor. This compressor is located at the upper stage of the cycle. Okay, and then at stage 4, it is the peak or the highest value of enthalpy, and then it will release or reject or remove heat to the surrounding by using the condenser between state 4 and state 5. State 4 and state 5 is where the heat is rejected to the surrounding. And and then after it exits the condenser, it will pass through the expansion valve to reduce the pressure. Okay, at the state 6, the what we call, okay, the refrigerant is in the saturated mixture condition. Okay, saturated mixture condition. Okay, this is saturated mixture. So we know the saturated mixture is consists of saturated liquid plus it's not a saturated liquid plus vapor. Okay, so we have a fraction which is mg over mf plus mg. If you recall back what is mg and what is mf, mg is mass of the vapor and mass of the liquid. Okay, so from the state 6, it will separate the 100% vapor and 100% liquid. So all the vapors from the flash chamber will go to the state 3, and all the liquid from the flash chamber will go to the state 7 here. So the cycle will go on until the system is shut down. Okay, so that is the basic principle of the multi-stage compression refrigeration cycle. Okay, this is the example. I will show you how to calculate or to analyze the multi-stage compression refrigeration cycle. Okay, consider a two-stage compression refrigeration system operate between the pressure limit of 0.8 and 0.14 MPa. So you write down this is 0.8 MPa. This is the 0.14 MPa. Okay, 0.8, 0.14. Okay, the working fluid is refrigerant R134A. The refrigerant leaves the condenser as a saturated liquid and is throttled to a flash chamber operating at 0.32 MPa. So now we know this is 0.32 MPa, this pressure line. Okay, part of the refrigerant evaporates during this flash process, and this vapor is mixed with the refrigerant, leaving the low pressure compressor. Okay, so it says that vapor will be mixed with the refrigerant from the low pressure compressor here from state 2. So state 9 is the summation of vapor from state 3 and state 2. The liquid in the mixture is then compressed to the condenser pressure by the high pressure compressor. So this is the process where the mixture will be compressed by high pressure compressor. Okay, the liquid in the flash chamber is throttled to the evaporator pressure and cools the refrigerated space as it vaporizes in the evaporator. This sentence is basically trying to explain the process from the state 8 to state 1. It absorbs heat from the refrigerated space using the evaporator between state 8 and state 1. Okay, and then assuming the refrigerant leave the evaporator as a saturated vapor and both compressors are isentropic. So these are important information. The state 1 is saturated liquid, like what is shown in this TS diagram, and all the compressors are isentropic, means that S1 or entropy 1 will be equal to entropy 2. Similarly to this process, S9 will be equal to S4. Entropy 9 equal to entropy 4. Okay, so A, the fraction of the refrigerant that evaporates as it is throttled to the flash chamber. Okay, the question A wants you to find the fraction. What is the fraction? Fraction is the symbol of X for the saturated mixture. Okay, so the fraction of the refrigerants that evaporate as it is throttled to the flash chamber. So what the question 1 is the fraction value here. So I put it as 6. So the question A wants the value of at 6. Okay, and then B, okay, put it at 6. The amount of heat removed from the refrigerated space, okay, amount of heat removed from the refrigerated space happen here between 8 and 8 and 1. So H1 enthalpy 1 minus enthalpy 8. And you must multiply with the what we call here the mass flow rate of the lower cycle. Okay. Um, let's say all the system is equal to 1 mass flow rate. So after it separates between state 3 and state 7, if here I put the variable x, as it will confuse with the fraction. Okay, never mind. Here we have x6. Here I just put it x. And if here is x, so for the lower stage, it should be the remaining between 1 and x. Okay, so here is 1, here is 1, here is 1, here is 1. So after it reduced to the x here, so the value at 7, 8, 1 and 2 will be 1 minus x. Is it correct? So here 1 minus x. Here also 1 minus x. 1 minus x. And at this mixing chamber, 1 minus x will be mixed with the x, so it will plus with x, basically will become to 1 like this. Okay, so the QL must be multiplied with 1 minus x. Okay. So x6 here also equal to the x value here. Okay, so I put it at 6 here. And okay, and the compressor work per unit mass of refrigerant flowing through the condenser. Compressor work per unit mass of refrigerant flowing through the condenser. Okay, so the value of compressor, which is work in, will be equal to total compressor. Here we have two compressors, so we have sum or total up the high pressure compressor and low pressure compressor. Okay, it is straightforward. So high pressure compressor is between the state 4 and state 9. So to find its work in, we'll need to find the enthalpy change between H4 minus H9. And you have to multiply with the fraction. So here we have fraction 1. Okay. Plus, this one is high pressure compressor. I put it the short form HPC. Okay, plus with the low pressure compressor H2 minus H1, but you have to multiply with the fraction here, which is 1 minus x. Okay, so the last question, C, the coefficient of performance. So C is the COP. So the value of COP can be determined by the QL over work in total. So here is total. Okay, this one is QL. So you have to get the value at 6, and then you have the at 6 value and the enthalpy value at every state, and you will get the QL work in, and finally using QL and work in you can find the COP. Okay, so uh, as our normal calculation, find the properties at every state. Okay, so let's try to find the value. I will pause this video and I will show you after I get all the enthalpy values. Okay, so this is the values from the book. Okay, you have to find the enthalpy at every stage and compare your values with these values here. If you have problems, let me know and I will show you how to find the enthalpy value. Okay, but please do it first by your own. If not, you will not learn anything from our lessons here. Okay, so basically the state 1 is saturated vapor. So H1 equal to HF at that pressure. So pressure 1 is 0.14 MPa. And state 2, P2 equal to 0.32 and entropy 1 is also SF at 0.14 MPa, and entropy 2 is equal to entropy 1. Why? Because it is isentropic process. And using this value, you can find the enthalpy 2. Here it is superheated. How I know it is superheated? Because here in the TS diagram, the state 2 is the out of saturation region. Okay, and state 3 is state 3, you have to find using the saturated mixture formula, which is H3 equal to HF plus at6 HFG. Is it correct? Okay, I check it first. Okay, it is correct. So you have the value H3 here, and for the state 4, it is also superheated. P4 equal to 0.8. Okay, entropy 4 equal to entropy 9. So you have to get the value of entropy 4 first before you can find the value of enthalpy. To get the entropy 4, you have to finish the state 9 first. Okay, let's KIV it first. We complete it step by step, state by state. Okay, at state 5, where is state 5? Okay, state 5 is saturated liquid. So H5 is equal to HF. Oh, sorry, this is Hg. Okay, at that pressure, what is the pressure of state 5? It is 0.8 megapascal. Okay, state 6, H6 equal to H5. So after you have the value of state 5, straightforward, you will have the value of state 6 here. Okay, and state 7, by referring to this TS diagram, state 7 is saturated liquid. So H7 equal to HF at that temperature, So state 7, the pressure at 7 is equal to 0.32 MPa. Okay, here 0.32. And state 8, H8 is approximately equal to the H7 because this is the throttling process. And finally, the state 9 here. Okay, state 9 we have the pressure 9 equal to 0.32 MPa. Okay, this is special. Please take attention. At state 9, this is the mixing chamber. So, let's say I draw here. Okay, the exit of the mixing chamber here, the state 9. So we want to find the value, enthalpy value of state 9. Okay, before the mixing chamber, there is refrigerant comes from the state 2 and also come from the state 3. So for the energy conservation, energy in equal to energy out. Okay, so this is the first law of thermodynamics. So H9 out will be equal to the in. In consists of enthalpy 3 and enthalpy 2, right? But please remember here we have the fraction at 6, but for here we have the fraction 1 minus x. Okay, and here we have the fraction of 1. So H9 multiply with its fraction 1, and H3 is the at 6, and H2 is 1 minus at 6. Okay, so to get the value of H9, you have to use this equation. Okay. Similarly to the S4, S4 is equal to S6, S4 plus 1 minus S6, S2. Okay. And first we have to find the x6. Okay. If you want to find H6 here is equal to H6 equal to H5 here, right? Okay, H5, let's say you find using the properties table, you will get 95.47. Okay, so here is 95.47. Okay, using the saturated mixture formula, H6 equal to HF plus at6 HFG. Okay, this formula we have learned in the MEC351 thermodynamics. Okay, so by using the properties table, you will find the HF at that pressure. Okay, let's try look at the properties table. Refrigerant A11 and A12 for the pressure. Okay, state 6, the pressure at the state 6 is equal to state 6 here equal to 0.32. I forgot to put P6 equal to 0.32 MPa. Okay, so 0.32 MPa here, 320 kilopascal. The value of HF is equal to 55.16 plus at6 HFG is 196.71. You rearrange this equation, you will get the value of at6 equal to 95.47 minus 55.16 divided by 196.71. So you will get 95.47 minus 55.16 divided by 196.71. So you will get 0.2049. It is dimensionless because it is a fraction, so there will be no unit here. So this is the results or the answers of fraction 6. So let's continue with the question B. Question B. Okay, you have to find the QL. QL happens between the evaporator here, between the state 1 and state 8. Here is QL. So the QL equal to H1 minus H8. But you have to multiply with the fraction here, which is 1 minus x. So 1 minus x6. Okay. One minus x6 H1 minus H8. So 1 minus 0.2049 multiply with the H1. Where is H1 value? Okay, 239.16 minus H8. H8 55.16. So QL equal to, okay, this is the unit in kilojoule per kilogram, and for the fraction we don't have unit, so the unit will remain kilojoule per kilogram. Okay, so I have 146.2984 kilojoule per kilogram. Okay, and now we have to find the work in total. We have two compressors. One is for the high pressure compressor, and the second one is the low pressure compressor. But bear in mind, high pressure compressor, the fraction is 1 here. If you don't want to put 1, it also okay. But for the low pressure compressor, please don't forget we have 1 minus x fraction here. Okay, H2 minus H1, but we have the fraction 1 minus x. So you have to multiply to 1 minus x. So this is the low pressure compressor. Also, you have to add with the high pressure compressor. High pressure compressor between the state 4 and state 9. So H4 minus H9 times with 1. The fraction at the upper stage is 1. Okay, so you substitute with the enthalpy value. H2 255.93 minus H1 239.16 multiply with 1 minus at 6 here, so 1.2049 and plus with H4 minus H9. H4 value is 274.48, right? Okay, H9 255.10. I check. Okay, so wait a second, I use my calculator. Okay, so I get 32.7138 kilojoule per kilogram. Okay, so finally we can calculate COP. COP is the QL over work in total 146.2984 divided by work in 32.7138, and finally we will get wait a second, I use my calculator first. Okay, I get 4.47 COP values. Okay, so that's all the tutorial how to analyze the multi-stage compression refrigeration cycle. Okay, so I put another example equation in our Google Classroom. I hope you can do by your own and submit your solution by sharing the links to the picture that you take using your handphone. Okay, so that's all for today. So this is also the end of the chapter 1. Next time, for our next class, we will learn the chapter 2. Okay, if you have any other question or problems, let me know. Ask me in the WhatsApp group. If I have time, I will try to answer all your questions. So that's it. Thank you. Assalamualaikum and good morning. Bye bye.